Hi everyone. Can someone in the chat tell me if you can hear me? I know there's a 30-second delay, so I'll wait a little bit. It turns out that there's only 4 people out of 10 in the stream. I was expecting the class, most of the class to be there, but I don't know. So if someone can just let me know in the regular chat here whether or not in the text chat whether or not you can hear. Okay, excellent. Yay. Well, there's only 4 people, but let's do it. Let's do it, okay? I know you can watch these later, but there's nothing like being here with me while I do it so that you can ask questions. And so, well, let's begin. First thing I wanted to tell you, I mean, I've said it already, but it bears repeating that, I know that your classes are an hour and a half each. Well, I guess an hour and 20 minutes each. And I gave you 2 hours of video to watch. And there's just no way for me to really fit the topics into the sizes of the class. I mean, I could have tried, but it would have chopped things up in a very strange way. So each of my video lectures is actually going to be an entire topic. And that means that sometimes it'll be short, sometimes it'll be long or whatever. But what I'll promise you is that I will never go over 3 hours total, including the live stream per week. That's what you would have had in the classroom. So because you did 2 hours of viewing of lectures, I'm just going to limit this live stream to 1 hour. In fact, in the previous class, it was more like 45 minutes. So, I will never expect you to commit more than the 3 hours that you would have committed in the classroom. I think that's only fair because I don't want to keep expanding the time that you have to commit. Nonetheless, having said that, I'll only limit your contact time to 3 hours. If you need me for more than that, don't hesitate. I mean, you can email me in the evenings. You know that I have Google Hangout every single evening. You can always ask me questions during Google Hangouts. If those times are no good, I pick 7:30. A lot of people like the 7:30 time slot because they're just available at that time. You work during the day. If that's not a good time, feel free to email me. Google Hangouts are very easy to create. If you have a question, you could just email me. If I happen to see it, I can create a Google Hangout and we can get together. Of course, you could always just email me the questions. So there's lots of ways to get a hold of me. Also, those assignments that you have that I'm giving you weekly, they have no time limit on them. So, if you start one and you get in the middle of it and you don't know how to answer a particular question, just leave it off and you can ask me a question and then I can help you with that. Okay. So, well, I just wanted to explain that because, we're going to have this situation where, sometimes you're going to have less than an hour and a half of viewing and sometimes more than an hour and a half. This particular week it turned out to be more than an hour and a half, but like I said, I'll always keep your time commitment to 3 hours. Let me know if this is an inconvenience to you or if there's a problem, because I'm kind of new at this too. Okay, I mean, I have experience from last semester teaching online, but if you're seeing any kind of difficulties with this, feedback is more than welcome. Okay, having said that, what you should have watched up till now are 2 video lectures. One video lecture was on 1D kinematics under the assumption of constant acceleration, and the other one was 1D kinematics, um, uh, simple harmonic motion. Okay, and there I presented you with some problems, and they were kind of polished problems. And so, since they're polished problems, you don't see all the steps that I do to solve them. And so that's why I wanted this kind of interactive live stream because physics really is about solving problems. It's conceptual questions too, but there's a large portion of physics which is about solving problems. So I want to make sure that you actually watch the way I solve them. In particular, today with the first problem, you're going to see me how I develop the diagram. Okay, again, during the lecture that you saw online earlier, the pre-recorded lecture, it was all the diagram was all done. But the diagrams are usually created in certain steps, and I think it's important that you see how I do that. So that's what we're going to do today. Okay, so just before I begin, every once in a while you'll see me switching over to the chat here, and like I said, 30-second delay, so there's a bit of a lag, and I guess this is a disadvantage over Zoom, but the advantage is everything's recorded and you can watch it over and over and over again. But I don't see any questions, so let's go on. So my first question doesn't cover everything that I did in 1D uh, kinematics constant acceleration. Okay, in particular, what I'm missing in this one is uses of the quadratic. Okay, you will see that on the assignment that I give you next week. There'll be two questions on 1D kinematics for constant acceleration, and I want to make sure that you can solve that quadratic. But I decided for this one that I would do something just a little different, just to show you, how to reason through I wouldn't say more complicated problem, but a problem which is more conceptually demanding. If you could do this one, then you're probably good for all the problems. Okay, so what's this problem? Okay, this is problem number one. Problem number two, by the way, will be on an oscillator. So, okay, so problem number one, a rock is dropped from the top of a skyscraper. So you're in a very tall building, you drop a rock, okay? And I wasn't clear here if you throw the rock down. I'm just going to assume that you just drop it from rest like that. On a test, by the way, I'm very careful with my language, okay? But because we're doing this together, I can be a little bit more relaxed, okay? But yeah, we just drop from rest a rock from the top of a skyscraper, and of course it starts to fall, okay? And it's going to pass by two windows. It's found that it's falling at 10 meters per second when it falls past the first window, and it's falling at 50 meters per second when it falls past the second window. Okay, and I ask you two questions. The first question, part A, is how far apart are the two windows, and question B is how long does it take for the rock to fall from one window to the other. Okay, so how do you do this? Well, you start off by drawing a diagram. Okay, and there's a couple of steps in drawing a diagram. This first step is you just draw what I described here. Okay, so just draw, like, a skyscraper with two windows and a rock falling. Okay, and then step number two is going to be adding the coordinate system. That is adding a ruler, so you could see how things are measured on that ruler. And there's some choices in doing that. So you want to make the best possible choice that makes life easy for you. And then step number three is identifying the numbers that you're going to plug into the equation. Typical error that's made by students is you'll go straight to the equations to try to plug in the numbers. You could get confused. You could make a mess of things. It's best to do it this way, okay? And what you should be picturing is that we're really doing an experiment. Now, we're not really, because we're not in a lab, but you think of this as if you were doing an experiment. What would you see? So you picture it in your mind's eye and you draw it. Okay, so I'm going to switch to a whiteboard here like that. Let me see, did that work? Good. All right, and let's start off by drawing a picture. Let me start off in black here. So there's my skyscraper like that. Okay, and there are two windows. There's my first window. Okay, I guess I can call it window number one, like this. And then here's my second window over here like that. Okay, and we can call this window number two. All right, and here I am at the top of the building, and there's the rock. I'm going to release it from rest, and of course, what's the rock going to do? It's going to fall to the ground like that. Okay, so there's my rock falling down like that. Okay, and all right, well, there's the first step. I drew as closely as I could what I described verbally in the problem. Okay, I didn't put any numbers down or anything like that. I just draw a raw picture of what you would see. All right. So what's the next step? Okay, the chat here. Okay, what's the next step? The next step is to, I called it a coordinate system. It's basically like putting a ruler there. But there's two parts to it. There's the ruler and the stopwatch, okay? And so here's the ruler. I'm going to draw the ruler in blue. And my ruler is going to, like it's got an end here like that. And it goes up like that, okay? So I know I'm drawing a line, but just pretend that this line is a ruler. And I'm going to put an arrow at the top here because that's the positive direction, okay? That's where the numbers increase. The numbers increase upwards like that, okay? So smaller numbers at the bottom, bigger numbers at the top, okay? Now, we're not quite done yet because we have to choose where the zero is, okay? That's the origin, like in the example that when I first introduced 1D kinematics, that was like my tree. Or I could choose the zero down here at the bottom, or I could choose the zero at one of the two windows. Now this is actually an interesting thing because you get to choose where that zero is, all right? You actually get to choose the orientation of the ruler too. You could have the ruler going positive down. I'm not going to do that. I think it confuses things, so I'm going to just leave, whenever things are falling, I'm going to make up positive, okay? That means that things that are going down are negative, all right? And let's choose our origin. Now, you could choose the origin at the ground level, but then if you did that, you go, well, I don't know how high window number two is. I don't know how high window number one is. So I'm going to choose the origin at one of the two windows. You could choose it at window number one, but I'm going to choose the origin right there at window number two, okay? And you say, well, will you get a different answer if you choose it number 1? Yeah, actually, your value at the end would be different, but the final verbal answer, like when you do the numbers, they'll be different. But when you come up with a final answer, it will be the same. The distance between the two windows will turn out to be the same. So it doesn't matter where you choose the origin, but I'm going to choose the origin right there, like that. Okay? So if that confuses you, remember you have a choice. You could choose it up here at number 1 or number 2. I'm going to choose it at number 2. It just makes life easier. And when you get good at these, you'll see why it makes life easier. Okay? So quick look at the chat. No extra questions. Okay, let's go on. All right. And so this is sort of step number 2. Okay. And for step number 3, I don't know. Let's do it in red here. Now that we have a ruler and you actually have a stopwatch as well. Okay. What you're going to do is you're going to put some numbers down. And I guess maybe I should say, where is the thing at t equals 0? So I'm going to go back to my blue and I'm going to say t equals 0 because there's not only an origin in x in the position, there's also an origin in time. So imagine this rock is falling. And you say, okay, when do I start my stopwatch? You know what? I'm going to start my stopwatch right here, right at window number 1. So when it passes window number 1, that's going to be 0 seconds like that. Okay. So when the rock is right there, okay, right there beside the window, that's t equals 0 seconds. Okay. Now maybe I have a friend down here at window number 2, and the two stopwatches are in sync. So it's at 1 second there, and then at a later time it's down there, but we don't know what that later time is. Okay, we don't know. So I'm going to say t is equal to question mark right there. Okay. All right. So now we're going to start looking at the numbers that we can put in there. And before I do that, let's go back to my this screen right here. And let me show you the equations that you're going to use, okay? Because the equations have some symbols in it. And I guess step number 3 is to look at that diagram and identify the value of each of the symbols that go into the equations as best you can, okay? So over here, let me scroll that up, okay? Here are the 3 equations. I just cut and paste that from another window. Here are the 3 equations that govern 1D kinematics, constant acceleration. Okay, and by the way, if I didn't mention it already, when things fall, they fall under constant acceleration. Things speed up at the same rate as they're falling. Okay, so there's equation number 1, there's equation number 2, and equation number 3. Let's go through what each of the symbols mean, and we're going to go back to the diagram and look at the diagram and see if we can identify in the diagram what the values are for each of the symbols using our ruler and our stopwatch. Okay, so there's this x naught. That means the initial position. That means the position where it is measured off of the ruler at t equals 0. There's v naught, and that means the initial velocity. That means how fast is it going at t equals 0. Okay, and then there's x over here, and that means where is it after a time t. That's basically the position of our window, so window number 2. Okay, so where is it at time t equals at a later time? Okay, so that's sometimes called the final position, or the position at time t. Okay, so we've got an initial position, an initial velocity, a final position, and there's also a final velocity, and that's just called v. Okay, so we've got 4 so far. The little knot there, the little circle, means initial. So initial position, initial velocity, final position, final velocity. Okay, then there's 2 more. There's the time, and that's time between the initial and the final, and a, which is the acceleration, and there's only one a. There's no initial and final a, and you go, why? Constant. It's constant acceleration. Okay, things do not speed up or slow down. All right, and you actually know a because a is the acceleration due to gravity on the surface of the earth. Now, I didn't say here on the surface of the earth, and unless I say on the moon and I give you what a is on the moon or whatever, just assume you know that there are skyscrapers on earth. I don't know if there are any skyscrapers on the moon, but it's the acceleration due to gravity on earth. Okay, so over here, let me just write down that value a. It's technically equal to 9.8 meters per second squared. I'll say a little bit more about the units in a minute, but for our problems, you know what we're going to do? Just to make the math really easy, the arithmetic easy, we're going to approximate that to 10 meters per second squared. Okay, so I did mention that in the lecture that you should have watched, but I'm mentioning it again here. You shouldn't do this in the lab. Okay, this is fine in the lecture because we just want to make the arithmetic easy. We don't want to carry a bunch of decimals. In the lab, you can measure the acceleration a lot better than that, and you will. Okay, and so don't in the lab make sure that you use the correct the correct number. Okay, and I think I forget now if it's lab number 3 or whatever, you're actually going to measure a, and so you'll be measuring your acceleration due to gravity. It better come out to like 9.8 something. Okay, and you better do better than you should do better than just 10. Okay, but anyhow, for this purposes, we're going to round it off to 10. Okay, so keep these symbols in mind. There's initial position, initial velocity, final position, final velocity, acceleration, and time. Okay, let's go back to my whiteboard and let's see if we can identify them. Okay, so initial position, where is that? That's right here. Let me do that in red. Okay, so right here, this is the initial position. Why? Because that's where t equals 0 happens. T equals 0 happens at window number 1. So initial position, that's our x naught. Okay, and you say, well, do I know that? Well, if you look at the ruler, you really don't know any of the distances here. You don't know how high the building is. You don't know how high window number 1 is. Window number 2, you don't know how high it is above the ground, but you do know that window number 2 is at x equals 0. Okay, so that'll be the next one. But this one, x naught, the initial position, that's unknown. In fact, that's what you want to calculate. You're going to want to calculate x naught because you're going to want the distance between these two. The first window is at x naught. The second window is at x. And do we know x? We do. It is 0 meters. Okay? Like that. All right? So make sure you understand this. Because I chose the ruler there to be 0, well, of course, if I were to measure the position of window number 2, it's at x equals 0 meters. Okay, again, I could have chosen the 0 elsewhere, but I chose it here because you see how it made my life easier. At least I can say the position of window number 2 is x equals 0. We don't care how far the ground is. Okay, that's not part of the problem. We just want to know how far it is between these two windows, and so why not choose x equals 0 right there? We could have chosen it up there as well, in which case x naught would have been 0 and then x would have been unknown. Either would have been perfectly fine. I'm just going to pick this choice. If this choice confuses you and want to try the other way, try it afterwards. And if you can't get it, I mean, I can always help you during office hours, but you could try it the other way if you feel that that works. Okay, so that's our initial position. That's our final position. Okay, looking in the chat here, I got to switch windows when I do that, so a bit of a delay. Okay, good. All right, now initial position, final position, initial velocity, and final velocity. Okay, initial at t equals 0. What is it? Well, if you read the problem, I did tell you that it was 10 meters per second, but we have to be careful. Yeah, it's 10 meters per second, but what? There's a sign here, and if you don't put anything there, of course the sign is positive. But we're going to choose in our problems up as positive. Okay, up as positive. But which way is the ball or the rock falling? The rock is falling down. So when it passes window number 1, it doesn't have a positive 10 velocity. It has a negative 10 meters per second. So watch that, because I never try to be tricky in my problems, but I do want to make sure that you understand what the meaning is of positive and negative signs here. If your ruler grows positive up and you are falling down, then you need a negative sign. In 1D, there's only two directions. In this case, up or down. Up is positive, down is negative. Which way is it falling? Down, negative. Okay. If I'd thrown it up, then at the moment I'd thrown it up, because it was moving up, it would be positive. But in this case, when it falls past window number 1, down, negative. It falls past window number 2, down, also negative. Okay. And if you look in the problem, when it passes window number 2, I said 15 meters per second. Of course, down, so it's going to be negative 15 meters per second. All right. Okay, great. So we have initial position, we have final position, we have initial velocity, and then final velocity. Okay. Two more things are the time, and I already wrote the time here. The time when it passes window number 1, that's 0, because that's when we start our stopwatch. I mean, imagine you have a stopwatch, and as soon as it passes window number 1, you click the button, there's t equals 0. When does it pass window number 2? We don't know. So t is unknown. That's another unknown. And so we'll just write t equals question mark. And what about the acceleration? Well, the acceleration is the acceleration due to gravity, which I just told you a minute ago is 10 meters per second squared. Okay, and I'll tell you the units in a second. But got to be careful with the sign here too. Which way are you being accelerated? Which way are you being pulled with gravity? Down. And so even the acceleration is negative, okay? So the two velocities are negative and the acceleration is negative. If you get the signs wrong, you'll get totally the wrong answer, okay? So make sure that you understand where, like just to be, we could have chosen down as positive, but nah, let's not do that. Through this entire course, whenever we throw things, or whenever things are falling, up is positive, down is negative, okay? And so you fall past window 1, negative. You fall past window number 2, negative. You're being pulled down, you're being accelerated down, negative, like that. Okay, so there you go. You've got all those quantities there. And now that you've got that in this diagram, you can transcribe that to the, or you can write it into the equations. Okay, and so let me switch back to this other whiteboard here, like that. And I know I wrote that, but remember it's going to be actually negative 10 meters per second. And let me just cut and paste in. I've got another window here, and I've got that. Whoops. And then the only other unknown is t is also unknown. Okay, so all right, so after you draw the diagram, so draw a diagram without a ruler, draw a diagram with a ruler, and I guess with a stopwatch too, showing the initial and final time. Then try to identify the values off of that diagram. So like the initial position was unknown, the final position was 0, the initial velocity was negative 10 meters per second, the final velocity was 15, and the acceleration, of course, is due to gravity. It's negative 10 meters per second squared. Now you can look at what you know and the equations and decide which equation you want to use. Okay, so quick look at the chat here. Everyone looks like you're doing okay. Okay, so let me continue. All right, and how do you choose which equation? Well, let's see what we want to solve for. Question A is how far apart are the two windows? Okay, so we really want to solve the difference between x and x naught. Now, x we know is 0, and so we really want x naught. X naught is how high above window number 2 window number 1 is. Window number 2 is at the 0, okay, and window number 1 is at x naught. You get x naught and you find out how much higher window number 1 is over window number 2. Okay, so we're actually trying to solve for x naught. So your equation had better have x naught in it, otherwise you can't solve for it. Okay, so if you take a look at equation number 2, it doesn't have an x naught. Okay, equation number 1 does have an x naught. Now it doesn't have to be on the left hand side, because you can rearrange these equations. Okay, so don't think that you have to find a left-hand side isolated x naught. But the problem with equation number 1 is that it involves time, and you don't know the time. Okay, and so if you try to use equation number 1, x naught would be unknown, but so would the time. Okay, well, whenever time is unknown, that's when you want to use equation number 3. If you take a look at equation number 3, you know everything there, except x naught, which is what you're trying to solve for, actually. Okay, so yeah, equation number 3 is the one you want to use. Okay, equation number 3 is actually equation 1 and 2 combined to eliminate time. So it's not like it's a, how should I put it? It's not a new equation, but it makes life really convenient, because as soon as you have a problem with where time is unknown, you say equation number 3. Okay, I mean, almost without thinking, and you will definitely have enough information to solve with equation number 3, else I did something wrong in setting up the problem. Okay, and I don't know if I've ever done that, but they're simple enough for me to get right. Okay, I guess I could always make a mistake, but barring any mistake on my part, if t is unknown, equation number 3. Okay, so let's do that. Let me get equation number 3 here, and let me actually just cut and paste the what you would substitute in. This is not very deep, so I don't think you need to see all the details here. I'll just cut and paste. So use equation number 3 to solve for x naught. Here I just rewrote equation number 3, so let's go over it. It's v squared. I can't do squared in my text editor here, so that little caret there, that little up pointing thing, that's how I do exponentiation. A lot of your calculators actually do that too. So this is v squared, that's the final velocity squared, is equal to the initial velocity squared, plus 2 times the acceleration times x minus x naught. Okay, so we have the numbers because we identified them, and so we're not, if we did everything wrong, there's no confusion at this point. And so what you do is for v here, sorry, my dog is barking because the mailman just delivered something and my window is open. So anyhow, the joys of a live chat, okay? But here for v, we know what v is. It's negative 15, so negative 15 squared. We know what v naught is. It's negative 10, so negative. Oh, I lost the square there. So should be a little 2 right there, like that. And so there we go. So negative 10 squared plus 2 times the acceleration. Technically negative 9.8, we're rounding it off to negative 10, multiplied by x minus x naught. X is 0, x naught, there's your unknown. Okay, so now just take out your calculator. Negative 15 squared is 225, negative 10 squared is 100, plus 2 times negative 10 is negative 20, but then there's another negative here, so it actually turns out to be positive 20. Okay, like that. And then you just solve for it and you get 6.25 meters. Okay, so that's the answer. That's the distance between the two windows. Let's go back to the diagram for a second and make sure we understand why, if that makes sense. Okay, so here we are back at the window here, and I don't know, I've got colors, so I might as well use them. If this window here is at, oh, I need a darker green than that. If this is at 0 here, like that, I already drew the 0. This, if I were to read it off of there like that, read off of my ruler, I'd read 6.25 meters, like that. That's what I would read off of that ruler there, like that. Okay, that's an awful M. Let's try that again. Okay, there you go. Okay, so that answers the question. Obviously, if that's 0 and that's 6.25, the distance between the two is 6.25 meters. Okay, so any questions? Let me look in the chat. I mean, people seem to think this is fine. So this is actually a little bit on the easier side, mostly because it doesn't have the quadratic. But the reason I chose it, the reason I wanted to do this one, is because I wanted to show you how I went through the diagram identifying the values before I plugged into the to the equation. So I thought maybe a simpler example might be better. Okay, but make sure you know how to use that quadratic. And like I said on the assignment next week, you will need that. Okay, now that answers question A. And question A was, what's the distance between the two? Okay, how far? And this question B is, how long does it take the rock to fall between the two windows? In other words, we want the time. Okay, and so now if you take a look at our equations, now you want an equation with time. So definitely don't use equation number 3. You could use either equation 1 or 2. Okay, either one of them would give you the answer. But you know what? Don't use equation number 1 because it's got the quadratic. You would actually get 2 numbers. You'd have to figure out which number you need, and you might do it just for practice, but there's no need to overdo it for yourselves. Just use equation number 2. Do you know everything in there? Well, you have the initial velocity. Yeah, that was negative 10. Do you have the final velocity? Yeah, that was negative 15. Do you have the acceleration? Yeah, that was negative 10. And out comes the time. Okay, it's really quite trivial. Okay, so I'm just going to cut and paste the answer right here. Okay, it's like just a couple of lines. All right, so, well, 4 lines, I guess. Okay, so we're going to use equation number 2, like that. And equation number 2 says final velocity is equal acceleration times t plus the initial velocity. Okay, so the final velocity was negative 15. The acceleration was negative 10. The initial velocity was negative 10. Those two being negative 10, that was a coincidence. Okay, if I redid this, I might have chose a different number, but just to show you that they're different. But yeah, it was just a coincidence that the acceleration is negative 10 and the initial velocity was negative 10. Okay, and if you solve, you get half a second. Okay, so it's half a second. Let's see if we can understand that, because I did this on purpose so you could see very clearly what the meaning of acceleration is. Let's switch back to the whiteboard. Okay, and if you take a look here on the whiteboard, we're at window number 1 at 0 seconds. We're at window number 2 half a second later. Does that make sense? Well, what does acceleration mean? What does acceleration mean? Take a look at the units. Well, let's go through all the units. Units for position are meters. Units are for velocity are meters per second. That's how fast you're going. You're traveling 10 meters. Every second you travel 10 meters. Every second you travel 10 meters. Or for 15 meters per second, every second you travel 15 meters. This one's 10 meters per second per second. That means that your velocity is actually changing 10 meters per second every second. So if you're at negative 10 meters per second and you're going to change by another negative 10 meters per second, 1 second later you go from negative 10 to negative 10, you go to negative 20 meters per second. Okay, so 1 second after you're at window 1, your velocity would be negative 20 meters per second. Well, that's 1 second later. How much do you think it would be half a second later? Well, it would be half of that, and it would be, instead of going from negative 10 to negative 20, you go from negative 10 to negative 15, okay? And that's why it's half a second, because half a second would get you an increase in your velocity of 5 meters per second. That's the meaning of acceleration. Acceleration is how much does your velocity change every second. Every second, you travel 10 meters per second faster than you did a second before. Okay, that's what acceleration is. So it's the rate at which your velocity changes. All right. So I went over this very carefully because students often confuse velocity and acceleration. Velocity is how fast you're going. Acceleration is how fast you're speeding up or slowing down, or the rate at which the velocity changes. All right. Looking at the chat here, I know you've got a 30-second delay, but I don't see any questions. So that's it. That's it for question number 1. Okay. And question number 1, again, was on 1D kinematics constant acceleration. All right. I'll probably give you 2 of these problems for the assignment and then 1 on the oscillators for a total of 3 questions. But each question might have multiple parts, okay? So beware, because it's like that on your first assignment. It'll be like that on your second assignment. Like 3, how should I put this? Like 3 problems, but each problem will have like multiple questions associated with it because I'll be asking different things. Just like now I asked for how far the 2 windows are apart, and then I asked for the time. You know, I might ask you for a few different things, okay, and walk you through different things that I want you to solve for the same problem, okay? And the whole point of that assignment is that when you get to the test, you know, like what you're going to see on the test is going to be very similar to what you see in those assignments, okay? So this way there's no surprises. All right. So let's move on. One more time, look at the chat here. All right. The second thing that we did was simple harmonic motion, 1D simple harmonic motion. So let's look at a problem on that. Okay. So this is on what are called oscillators, and oscillators are things that oscillate are everywhere. Okay. Like right now, inside your ear, there are these little cilia. That's how you can hear me. Because as I speak, eventually the sound gets to your speakers or your earphones, and that causes these little cilia to vibrate back and forth, and that vibration is a kind of oscillation. Okay, if you knock something and it wobbles back and forth, that's oscillation. If you take a pendulum, that's a string, and you tie a weight to it and you let it go back and forth, that's also oscillation. So things oscillate. There are many different places where things will oscillate. Okay, and so this physics is quite generic, and this is just oscillation in 1D. So it's along a line, but it's back and forth forever. One more thing I'll say about it is like in real life, when you hit something and it oscillates, it wobbles back and forth, eventually it stops. That's because there's friction. What I'm teaching you here has no friction, so theoretically it would oscillate back and forth forever. Okay, so let's do the problem, and I'll explain things about oscillations as we go along. So I say here an oscillator is found to have a maximum velocity of 15 meters per second squared and a period of 4 seconds. Okay, so let's start with the period. What's a period? So because this oscillator is oscillating back and forth like that, it goes back and forth, there's a time it takes to make one complete cycle. The time it takes for something to make a complete cycle is called the period. So in this case, the period is 4 seconds, and it's given the symbol capital T. Okay. In this case, capital T is 4 seconds. So if you start at one end of the oscillation like this, and you go back and forth like that, by the time it gets back to where it started, that's 4 seconds. Okay, so it'd be like 1001, 1002, 1003, 1004. Okay, that's your period, capital T. Okay, then there's a few maximas. All right, maximum velocity, maximum displacement, maximum velocity, and maximum acceleration. The maximum displacement is because the oscillator goes back and forth, it's symmetrical about the middle. The middle is called the equilibrium, and it goes back and forth the same distance on one side, same maximum distance on one side as the other side. That maximum displacement on one side, that's as far as it goes one way before it stops and turns around and comes back. That's called the amplitude. It's given the symbol capital A. Okay. Then also the oscillator, as it moves, I mean, at the endpoints it stops when it turns around because it's moving one way and then it stops and turns around and moves the other way. At the moment when it stops, the velocity is zero. The fastest the oscillator goes, Vmax, that happens in the middle. Okay, so over here at the end point, it stopped and it goes faster, 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 faster. Maximum velocity in the middle, and then slows down, stops, turns around, maximum in the middle, then stops. Maximum velocity occurs at the endpoints. Maximum acceleration occurs at, maximum velocity occurs in the middle. Maximum acceleration occurs at the endpoints. Okay, that's when it stops and turns around. So maximum displacement and maximum acceleration occur at the same place. Okay, you need to know that to answer some of these questions. So make sure you understand that. And I've got a diagram to show you that afterwards too. But let's go through this. So we have this maximum acceleration. The first question, I actually already answered it. At what point in the cycle does maximum acceleration occur? Maximum acceleration occurs. There's only two possibilities, either in the middle, that is at the center, or at the endpoints, and maximum acceleration occurs at the endpoints. Okay, so that answers our first question. Okay, our second question is, what is the angular acceleration? So this is the other thing, and the last quantity that you should know about, and this is the angular acceleration. It's actually related to the period. And if the math were easy, you wouldn't really need the angular acceleration, because that's not even what you measure in the lab. In the lab, you measure the period. But it comes up in all of our formulas, and so it's useful to define this quantity called the angular acceleration. And the angular acceleration is given the symbol omega. Let me cut and paste here like that. It's given the symbol omega, which I can't do in my text editor. Okay, I'm going to do W, but it's not a W because it's like a W. As you see how they have pointy bottoms, the omega is like two two O's like that, kind of like that. So it's kind of got a rounded bottom. So it looks like a W, but it's rounded like that. It's the last letter of the Greek alphabet. You do need to know what it, the omega, and you saw me draw it correctly in the notes and whatever, because on the test I'll probably have it right. I won't use W. So here I'm using W, but just understand that that's equal to omega. Just like pi, I can't do pi in this editor, so I'm just writing pi. Okay, so the relationship between the angular frequency and the period is the angular frequency, omega is equal to 2 pi over t. Okay, so this question is really easy to answer. You know t, and so you just substitute in there. Okay, 2 pi is, we'll just round off to 3 significant figures, 3.14 divided by 4 seconds. And normally I don't put the units in there because we're working only in MKS, but let me put the units in there and show you how it works out. Okay, and let me just cut and paste the answer. There it is. Okay. Oh, sorry, didn't get it all. There we go. Okay. And so we get that the answer is 1.57. Notice where the seconds is. The seconds is in the denominator, and so you get 1 over second or per second. And that's what a frequency is. It's like how often does something happen per second? How often does something happen per second? So 1.57 per second. By the way, you should know the unit hertz, written HZ. HZ and per second identical, okay? Now, the reason you should know hertz is because most instruments, like I assume that at some point in the future you might be working in a clinic, like if you become PTs or ESS and you're working in a clinic and you've got something that measures frequency, like an ultrasound machine or something like that. It is per second, but no one ever writes per second, okay? At least I've never seen that on a machine. Everyone writes hertz, okay? But hertz really means exactly the same as per second. It's like how many cycles per second. I mean, I don't know if anyone listens to car radio anymore, but if you listen to your car radio and you're listening to FM, like you tune into 94.5 and it says megahertz, okay, so that's million hertz. Okay, so there it is, cycles per second as well. So almost all instruments will have it in hertz. So you should know the unit, but it is the same as per second. Okay, so a little bit of an aside there, but basically that is your omega, and you're going to need that omega to solve all the other problems. So, in this multiple section question, I actually walk you through it. So you're going to need that angular frequency in order to get the amplitude. Okay. All right. Why? Well, before I give you the equations for this, I told you there were like 3 maximas in this motion. There's maximum displacement, that's capital A, amplitude. There's maximum velocity, and there's maximum acceleration, okay? And those three maximas are all related to one another through omega, okay? And so you say, well, what's the maximum amplitude? That's actually related to the maximum acceleration, which I gave you. All right, so if you take a look up above here, I told you what the maximum acceleration is there, okay? So it's 15 meters per second squared. And you say, is there a relationship between the maximum acceleration and the amplitude, capital A? And the answer is yes. It's this equation right here. And let me just cut and paste all this because it's pretty easy stuff. It's just a bunch of arithmetic. But this, A max is equal to omega squared times A, that relates your maximum acceleration to your maximum displacement or your amplitude, okay? So there's an omega squared in there, okay? Now, I didn't ask for the maximum acceleration, all right? I asked for the amplitude, so you have to rearrange this equation. You might memorize it this way, A max is equal to omega squared A, but you're solving for capital A, and so you need to rearrange that, so just divide both sides by omega squared. You get capital A is equal to A max divided by omega squared. Plug in the numbers and you get 6.09 meters. Okay, again, rounding off to two significant figures. Okay, and so there you go. There's the relationship between the maximum acceleration and the maximum displacement or amplitude. All right, now the question D is, what's the maximum velocity? Okay, by the way, another way I could have asked this question is, what's the velocity at x equals 0? Okay, and if I ask it that way, you got to be careful. It's slightly different. You need to know that maximum acceleration occurs at x equals 0. Otherwise, if you didn't know that, you would know to use this formula right here. Whoops. Too many windows open. There we go. You would know to use that formula because you say, well, you say velocity at x equals 0, and you say, well, I didn't give you an equation for velocity at x equals 0. I gave you an equation for Vmax, but Vmax is the velocity at x equals 0. So just make sure that you know at which point in the cycles all the maximas occur. Okay, and like I said, I've got a diagram at the end to show you that. So Vmax, the formula is Vmax is equal to omega A. Okay, again, you're relating your velocity one maximum to another maximum through omega, and just substitute in here. We know omega, we've solved for that above. We know A, we solved for that as well, and so that gives you that the maximum velocity that happens when the thing passes through the middle, that maximum velocity there is 9.56 meters per second. All right, and I'll look in the chat in a second, but we've answered the final question. At what point in the cycle does it occur? At equilibrium. In other words, at x equals 0, which is the same, or in the middle, all synonymous terms. Okay. All right, let me look here in the chat. No extra questions, so I hope that was pretty straightforward. These questions on simple harmonic motion, the theory was a little bit conceptually demanding because I drew all those sines and cosines. But when it comes to actually solving the problems, I think solving these problems are pretty easy, at least compared to the previous problem we did. Okay, so let me just show you one more thing. Where the maximas occur in the cycle, and then we're done with this lecture as promised, because 2 hours of pre-recorded lectures. We'll just leave this one at 1 hour for a total of 3 hours. Okay, so let me switch to this, and let me switch to this. Oh no, you know what, I think I didn't save it. Let me see if I saved it. If not, I'm just gonna have to redraw it. Give me a second here. I don't want to waste your time. Oh, there it is. Yeah, except that it's coming up in the wrong window. Let me see if I can switch windows very quickly here. Yeah, there we go. Okay, there we go. So yeah, it's not perfect, but it's good enough. Let me see if it's showing up right in the. Yep, it is. Okay, I just saw it appear. Okay, great. What's going on here? Well, take a look at the black. The black is the path. Now, technically, the path of the oscillator is just on a line, but it's hard for me to draw like, back and forth along a line. So I gave it a little bit of depth there. It's like it's making this kind of a cycle here like that. So it starts off, say here on the right hand side, and it goes to the left, passes through equilibrium, and then gets to the right, stops, turns around, goes through equilibrium, and then goes back and then does it over and over and over again. Okay, so where's the maximum displacement? That's at the two endpoints here. By definition, it's as far as you're going to get from equilibrium. So that's at x equals a, and on the other side, that's at x equals negative a. Okay. Now in these problems, we really don't worry about the positive and the negative. That's why you don't see like a coordinate system. But if you wanted to, you could say positive is on the right and negative is on the left. But usually, when we're solving, I just say solve for the amplitude. Okay. In which case, you just give the positive value. All right. So x is equal to a, x is equal to minus a. That's the furthest it's going to get from the middle. That's the maximum displacement. Where does the maximum velocity occur? Right at the middle, right there. So that's where Vmax occurs in the middle. Okay. At the endpoints, the velocity is 0 because it stops, turns around. Okay. So 1 minute it's going one way, the next minute it's going the other way. So if the sign changes, like from positive to negative, obviously it has to go through 0 and doing that. And so right at the endpoints, the velocity is 0. Okay. And finally, the acceleration. Where's the acceleration maximum? The acceleration is maximum at the endpoints. Okay, so the acceleration is maximum where the displacement is maximum, and that pretty much summarizes, where the maximas occur for an oscillator. Okay, so all right, there is a question. I see there. Is there any way we can get these questions beforehand so we can do them with you, or do you or do them beforehand and use the live streams to check the? You know what? I'm not sure because I kind of make these things up as I go along. Like I had them made up only a few minutes before. What I recommend you do is you can repeat them afterwards. So I'm gonna say probably not. That I don't think I can actually get them all ready for you beforehand. Okay, mostly because the live stream is something that I'm going to do on the fly. So I may very well change problems as I go along. Okay, today I just had to think up of two simple problems, but in the future I may actually just make up problems as I go along. So Timothy, I'm sorry, but I'm probably not going to be able to do that. But what I recommend is I'm going to give you problems to do in the assignment. Obviously you're going to do those. You can do variations on those. You can change the numbers and see what happens, or you can repeat the questions I did with different numbers and then ask me afterwards, either in an email or whatever. Ask me if you did it right. Okay, does that work for you, as possible, working through the possibility of working through problems? Like it sounds to me like you want more problems to work through, so I can definitely give you more problems to work through and check your answers. Okay, can you give us practice questions so that we can practice and make sure we understand during the live stream? Yeah, actually, that's actually a better idea. I can give you practice problems that you can try. So you know what? Let me do that right now. Zoe, good call there. Let me switch back to this, and geez, I wish it if you had been in my previous class, I could have done that for my previous class. So let's do this. Here's practice question number 1. Okay. Practice question number 1, and let me see how I'm doing for. Oh, there's lots of time. Okay, I'm actually going a little faster for you guys. So here's question number 1 that you can practice. I throw a rock. Oh, I'm on the top. I'm on the top of a building, 40 meters high. I throw a rock up with a velocity of, how fast should I throw it? I don't know, 30 meters per second. Okay. How long before the rock hits the ground? Okay. And how fast is it going when it hits the ground? Okay, there's a practice problem, and actually I like this idea. I'm glad you thought of it. The reason is, let me just move that down a bit so you can see it. Okay, you can write that question down while I go talk to you. I like this because actually, then I can create these problems on the fly and custom tailor them, and also I can cover some other possibilities. So this is another possible problem for you to do. Okay, and another one for the oscillator. I mean, they're so simple. I'm not even sure if I can create one that's much different. So, but I can give you this. I can say, so here's problem number two, and I could say, all right, let me make up some numbers. Uh, an oscillator is found to have amplitude uh, 1.5 meters. Well, let's make it 1.4 meters, and maximum velocity, maximum velocity, 25 meters per second. Okay, what is the period of the motion? Okay, and you know what? What is the maximum acceleration? Okay, there you go. There's a couple of problems. Um, is that good for you guys? Do you want? I don't know if I want to give you too many here. But this one problem, these two, and the problems I just did, pretty much cover the possibilities for you. Okay, is everyone else okay? All right, is everyone else fine? So or Zoe or anyone, um, if you want more possible questions, because you feel that you're not getting enough practice with these. So see, I guess in my mind, I'm thinking that you'll repeat some of the problems I do. So what you do is you could take the problems I did, not look at my solutions, and see if you can repeat them. Okay, and the numbers are kind of arbitrary. Change the numbers. See if you can still solve them with different numbers. Although changing the numbers is kind of minor. All right. All right, guys. If that's good, if there are no more questions, I'll wait a few minutes because of the lag. If there are no more questions, then we'll end the live stream. Okay, and I think what I'll do in the future is at the end of one of these live streams, I'll go over some problems that I want to go over. I'll give you some extra problems that you can go over. Feel free to ask me in any mode you like, whether you did it right or not. Okay. So I'm just typing in the chat here. Everyone okay? Can I end the stream? All right. Looks like people are happy. Okay. All right. Stream is ending. Bye-bye.